We've talked about this already, but whenever a function is below the x-axis, then that area under the curve always gives a negative number. So you're going to sometimes be asked the following question. Well, let's say I have a curve, I don't know, like this, and they say, can you add up all of these areas bounded? There's a difference between bounded by the curve and the x-axis and the question of asking the area under the curve. Because if this was the area, let's say I go, looks like, I'm going to say this is 0, this is 2, this is 3, this is 4. This area between 2 and 3 would actually be negative. And if I just found the integral, the definite integral from 0 to 4, it would take that into consideration. So if this was 2, and this was 2, and this was 3, it would say the whole area is 3 because this 2 and this 2 would cancel each other out. But you're going to get some questions that just say, can you find this area bounded by the curve and the x-axis? Then you would have to think of that part as positive, even though it shows up as negative. And you'd run into a problem if you just did the integral from 0 to 4. Now, there's two solutions to this. One, you can find each little section separately, which if you had a non-calculator, that's what you would need to do. And then we would need to put absolute values around the part that was negative to make it positive. If you had a calculator and were allowed to do the calculator, this actually works really nice with the absolute values inside. It's not so nice if you don't have a calculator because the absolute value of a function is not the easiest to integrate. But if you have a calculator, what does that absolute value of that function, what would that do? Well, the same curve that I had would now look like that because it would just reflect the bottom part up. And then when you found the area from 0 to 4, it would have positive, positive, positive. And it would work out very nice. Okay? So a good example of this would be if I take out my calculator, and in my calculator I just did cos x. Could work if I did cos x or sin x. So if we looked at this, this is my cos x graph from about negative 2 pi to 2 pi. Well, actually, it looks like it's going, yeah, this would be 2 pi right there. So if I wanted to find my area, second calculate my area, number 7, from 0 to 2 pi, one full revolution. Oh, I'm in degrees. This is not. Let's go to radians. If you are in degrees, our calculus doesn't work. The derivative of sine is not cos in degrees. It is in radians, but not in degrees. In degrees, you'd have to consider changing the angle to radians. So then you would have like a multiplied by pi over 180, 180 over pi kind of thing, and you'd have a chain rule, which you would have to apply. It's one of those things that kind of doesn't get talked about a lot when you're learning it. You just sort of assume that you just can do it all the time, but it does only work in radians. Anyways, let's go back. There it is. That's why I had, before this was 360 degrees, and I was like, why from 0 to 2 pi was it just a tiny little part? Because it only went to 6.28. So here now, if I do the integral from 0 up to 2 pi, 2 pi, there we go. I get e to the minus 14. We talked about this, the calculator being like, it got close enough, but it's basically 0. Notice that if I go back to my equation and I put absolute value bars around this, so I'm going to just, I don't know if there's a nice way I can insert the absolute value, I don't think so. Math over to number and add the absolute value, no. Cos x inside of there, delete these ones. So now my graph is cos of x. If I graph that, it's bouncing. And now my area between 0 and 2 pi is 6.28. It's 2 pi. Right? Can you see why? This distance, I'm playing around with, I shouldn't play around with math. But you see how you can take these two parts and flip them under? Can you imagine that making a perfect circle? If you made that a perfect circle, your radius would be pi over 2. And if you did pi r squared, would you get that as your area? Anyways, we'll play around with it. Think about it. It's kind of fun. So, if you have a calculator, the absolute value makes your life super easy. If it is a non-calculator, you're going to have to find these x-intercepts so you can break up your areas and find it separately. So here is, so find all of our x-intercepts, separate the integrals, and then solve each one separately. This is if you didn't have a calculator and we're doing it by hand. So if I wanted to find the area of x squared plus 4x from -2 to 0, if I just did the integral, does it make sense that that would be negative? But my x-intercept is at 0, and my other x-intercept would be at -4. So my whole area right now is below the x-axis. So if I found the integral, I'm going to get a negative answer. And because I know I'm going to get a negative answer, I've added the absolute value bars around it because the question was asking to find the actual area between the function and the x-axis. So when it's asking you to find an area, it wants a positive value from that. If it asks you to find a definite integral, then you would leave the answer as negative, because definite integral would indicate that that area was below the x-axis. But if it says find that actual area, anytime you're finding an area, that's a positive value. So we integrate. This one's not hard. Add 1 to the exponent and divide. Plug in your numbers. I love plugging in 0. So happy when one of the numbers is 0. It makes the mental math, I'm not going to say enjoyable, because I don't think figuring out something is 0 is like you don't get any sense of accomplishment from that. But easy, definitely. When you plug it in, get all of those values, and you get -16 over 3, and you're like, oh yeah, I want the positive value, so my area will be actually 16 over 3. Sometimes what I do on a question like this is when I get to the end and I'm like, ooh, it's a negative answer, I forgot it was supposed to be positive. Sometimes I actually go back and just like add absolute value bars around the whole thing and be like, oh, it worked out. They'll never know you wrote that late, that you did that after the fact. It's perfectly fine. So we take that absolute value to get the positive area. But now if we did the same question and they said, go from negative, is that too fast? That was too fast, right? You guys are still writing? Sorry, I'm excited. If we are going between -2 and 2, and we draw the picture, we're like, uh-oh, there's an x-intercept in here. there's an x-intercept in here, which means part of the area is going to be positive, part of the area is going to be negative. If we just did the integral from -2 to 2, we would get a completely wrong answer, and we wouldn't know how much negative got taken away from the positive. It's hard to tell from that final answer. Ooh. Hey, what's it called? Question from first semester. See how good your memories are. What's it called when I figure out that this point is -2, -4, and I would figure out that this point up here would be 2 comma, what was the question? X squared plus 4x? So this would be 2 comma 12, all right? What's it called if I know those two values, that I know there's an x-intercept between them? What theorem? Intermediate value theorem, right? Remember that? So by the intermediate value theorem, since the function is continuous, kind of makes sense. If you have to go here and get up here, you're going to have to, without lifting your pencil, you're going to have to cross the x-intercept at least once. You could cross it a bunch of times depending on the function, but at least once. So we would have to break it up. Now, preliminary stuff you might do is you might put y equals 0 into your equation, solve this by factoring, to say that I know that I have x-intercepts at x equals 0 and x equals -4, and then the awareness that in between -2 and 2, the x-intercept of 0 comes into play. Which we really can see by the diagram. So then we have to make this part positive, because it will be negative. And in fact, we figured this out in 8. And then we also have to calculate this part separately. Now this part we already calculated to be 16/3. Because I know you can do it, it would be no problem. We're not going to show any work, save us time copying things down. That area is going to be 32/3. And the whole area adds up perfectly to 16.
If ever there's a question that asks us to find a definite integral from A to B, do we put like unit square even if it's not asking for area specifically?
Oh, like if you're finding a definite integral, if there's no area, like there's no units given, they're never going to deduct for not having units. Okay? However, on your take-home quiz, if there was units given in something, I think there was one in feet that you did. Lots of you lost a half a mark for not writing feet squared when we found that area. So that, yeah. So if no units are given, it seems a little bit extra mean to deduct you for not including arbitrary units in the answer. But if units are given, please include the units. Everybody good here? Neil? Good? Yeah. Awesome. Perfect. Question, do you remember how to quickly graph using grade 12, x cubed minus 3x squared plus 2x? An x cubed graph, we could factor it to find x-intercepts at 0, 1, and 2. Because it's a positive x cubed graph, you know that its end behavior has to look like this, and it might have some curves in between. So if I draw those x-intercepts, and I have that basic shape, I can get this idea. Which means we're going to have a little area that's yellow and positive, then a little area that's green and negative, and a little area that is blue and positive. Again, if you want to double check this and you have your calculator, so you get, let's say you get your answer and you're like, I want to know if I got this right. You could do the integral from 0 and 3 of the absolute value of y dx. Do you see that y is all of that, and I'm lazy, and I'd much rather write the y than write all of the inside? That's perfectly fine. Of course, in your calculator, you'd have to type the 3x cubed minus 3x squared plus 2x. But if you did the absolute value inside, that would take this part and reflect it up, giving you that green area as positive, and you could check your answer, which would be way faster than what we're about to do, which is do each one separately and put absolute value bars around that green section in the middle once we've calculated it. So this is something that's going to, and obviously only on the calculator part of your exam, there are going to be some questions that if you use one method will take you 10 minutes. If you know shortcuts on your calculator, will take you 1 minute, right? 10 minutes versus 1 minute. If you know the 1 minute way, you save those other 9 minutes for those questions that just like honor tests where you want to pull your hair out because they're like over and over again, you're stuck. You'd want to bank that time. So we're going to try to know as many calculator shortcuts as possible. Anyways, again, I know you could integrate each of those, and I'm saving you the time by not showing you the work, because if I showed you the work, you know you would copy it down, right? You would. But I'm like, that's easy to integrate. X to the 4 over 4 minus x cubed plus x squared, easy to integrate. You could plug in the numbers, you would get it right. Here's the calculator showing each little part separately. And if you did the absolute value, you would get the 2.75. And again, units squared I have there, but you wouldn't need to have that in here. Okay, we get into some formulas now. Question? And if you don't need units squared, they're not going to deduct. And, well, I don't know. If they asked you what's 3 plus 7, and you said, the answer is 10 units squared, I'd be like, well, I don't know. If you put units squared where it's not an area thing, but yeah, for any area, I don't think they would deduct. They would just, at certain points, they just sort of ignore things.
So if you had a graph where the x-axis is like feet and the y-axis is seconds or time or something, when you integrate it, it would be feet squared, right? And x, whatever the x value is squared.
Okay. So whatever the x value is, if you integrate it, are you getting an area? I have to think about that before I answer completely. I'm not. But that is a good question. Okay. So, some new formulas. The picture makes it make sense. The question is, if you wanted to find the area from A to B, but somebody said, what could you guarantee that it has to be more than? And what can you guarantee that it has to be less than? That your area must be in between those two things. Does it make sense that if you found your minimum value, which I've showed with a little m, the little m is this point right here, multiplied by the distance, that would be this small rectangle. That small rectangle guarantees will be smaller than the integral. And if I find my maximum value, which I'll put on here as purple, from up to that maximum value would be capital M. Well, my area has to be less than the rectangle that goes up to the maximum. And so we can say that our integral has to be between this value and this value. And because it's bounded, we know that there is some number that exists in between there for the answer. Those are your bounds of an integral. Logically, should make sense from the picture. Next, we get to our mean value theorem of integrals. If you have a maximum value and you have a minimum value, and the fact that the function is continuous in there, there's going to be some value in the function in the middle where if you made a rectangle there, it would be perfect. In other words, you could draw any curve. Okay, I'm going to let's say I want to go from this point up to this point. Okay? That's my area under the curve. Since this is bounded below, we know that it has to be somewhere in between here and here. And since our graph is continuous, there's going to be a point somewhere along the lines where if I don't know, maybe it's here. So that this little area here that didn't get counted fills in this area there, and it works out perfectly. And it's like the mean value theorem that we've done before, but now it's the mean value for integrals. So again, it only works if the function is continuous. If it's broken up, we run into problems. There will always exist some number in between there that does that. Really easy to see for a straight line, right? If you have a straight line, you just pick the part in the middle to make this triangle the same as that triangle, and it would flip in there. But as I take this point, right, I put it there. As I move that point along, I'm like, ooh, no, I've got too much area that I'm not counting. Definitely at the minimum, this is a problem. But then, somewhere as I go up, now it's starting to split the difference, where that extra area above starts filling in the area that's missing until it's perfect. And there will always be, it would be impossible for there not to exist that value somewhere in there. Because at one point you're at the minimum, at another point you're at the maximum. Somewhere in between that minimum and maximum, there's that perfect value. And finally, if a function is continuous over an interval from A to B, the average value of the function is given to be, right, the area divided by the change from B. This is the average value of the function. Okay? Now, if we just took let's say I take x plus 1. Okay? This one, and I go up to, let's say I go just up to 3. 1, 2, 3. So here at 0, it's 1. And at 3, it goes up to 7. And since it's a straight line with a slope of 1, if you went up from 1 to 7, what would you say the average would be? You'd probably say it's right in between at 4. Let's check what happens if we find the average with the average formula. So, I'm doing integral from 0 to 3 of 2x plus 1 dx. And I'm going to take the average of this. I mean, 1 over b minus a. B minus a is 3. I guess I could show 3 minus 0 to plug in all my numbers. And check what I get as the result. This will be x squared plus x from 0 to 3. And if I plug in 3, if I plug in 0, again, it's really nice. 9 plus 3 is 1/3 of 12, which is 4. Which, because it's going up at a constant rate, it would make sense that the average is 4. Right? We could think of these as there are 4 students who did a test in my class. One student got 1, but this is not a good example. But one student got 1%. Another student got 3%. This student got 5%. And the last student got 7%. What is my class average? 4%. But what's interesting about the average of a function is this is like you had an infinite amount of students. As a really good teacher, they all scored between 1 and 7%. This is not so good, okay? But it's a nice straight line. But the beautiful thing about this formula is that it doesn't matter the curve. Like if you have an x cubed, it might have more values that are lower and more values that are bigger, or an x squared graph gets steeper quicker. So there's more higher values than there are lower values. This still finds the average of the function between 2 values. So now we'll do one with different values. What do you have to have memorized? You have to have memorized that if they ask for the average value, that you know that it's this formula. They ask for an average value of a function. And so from 0 to 3, that would be 1 to 3. And now our integral x to the 4 plus x squared plug in your numbers, you get 30. Ready? Another cubic function. We want to find the average value. So we do our average value formula. From -1 to 2 is a difference of 3. Set up our integral. And again, simple integral where you add 1 and divide. Plug in your numbers. And you get 4.25. So our average of our function is 4.25. And now we're going to try to find all the values of C such that the average value of f on the interval is equal to f of C. So we plug in, this was calculator question, which it is, have our equation in y1, plug in the 4.25 into y2, and you can find all of the places that it would intersect, including at 0. Oh no, sorry, this one's at -1.26. And we're only looking on the interval from -1 to 2. So you're only looking here to here. And you see that there are 2 places where that red line intersects.